Thank you. It's really an honor to be here. Thank you, Peter, for inviting me. That story, I think, is less important to you at this age, but in a few years you will be looking for a job. And I think my one piece of advice is that some of the best jobs are one of a kind. There's only one of them, and so people don't post them anywhere. And the only way you're going to find out about them is if you talk to people. My story isn't that exceptional, but I have one friend who finished her degree in an area between logic and computer science, which some people told her she would never get a job in. And she looked around and she felt that some of the things she would do would help speed up certain types of databases. So she tried to find a database company that might be interested in in her techniques. And she found a few, and most of them didn't answer her calls. But one of them called her and said, "How did you find us? We didn't know, we were looking for somebody like you, but we didn't know what it was called. We didn't know where to advertise. We didn't know anything. So how did you find us?" And so not only did she get herself a job, but she hired 4 other people from her advisor and other related professors, new PhDs, to go join that company. And this was 15 years ago, and it still exists. So anyway, I'm here to talk about the mathematics of image-based modeling. And I had a hard time deciding what to talk about because I've worked in a number of fields, and many of them are quite mathematical. So on the blurb mentioned that I've worked in modular robotics, bioinformatics, and currently I'm working on the image-based modeling and also a project about encryption. How do you search or compute on encrypted data, which most people don't know. Nobody in the world knows how to do that except in very special cases. So the point of this is that there are many projects that where there's some mathematical content, and I've been fortunate enough to work on many of them. So part of the reason I thought I would give a talk on this is because there's a lot of good pictures to go around. So this is going to be a talk on modeling, and modeling at the scale that we live at. So modeling this room or furniture, things like that. And one question that people ask is, well, why would you do that? And in a little while I'll get to some applications. But really the reason we're going to do it is that it's really easy now. So digital cameras are everywhere. People are taking photographs of everything. And computational power is really fast now. So you can render 3D things fast. And you can communicate about them because you have high bandwidth connections. So the things that were keeping us from doing this before were now past. So I want to just show you a couple things that people are already doing in this area with all those images. And this isn't work of mine, but I just thought it was really interesting sorts of things. So this is actually a video of a model, a very simple in a way model that people made from over 1,000 images they found on Flickr that are just publicly available. Many people had taken them, of St. Peter's Basilica. And they made this model by trying to match points in the various photos. And when they got a good match, they said, I know where this point is. And we'll talk in a little bit about how they do that estimation. I have an intern. I had an intern last summer who came to work with me on the stuff I'll be talking about later, who works with the people who do this. And she has a game now where she's trying to encourage people to go take photos that will fill in these models better. So another thing I wanted to show you was that instead of just showing what you can pull from these photos, you can do spatial photo browsing. So if you take pictures of a room and then can estimate where they came from, instead of just showing one after another without connection, you can put them all together like this, and you can go around and you can see where the edges of different people's photos were. And sometimes they don't stick together really well, but you can get a better sense, I think, of this building and the beautiful things here. And if I want to go to a specific image, I can click on it and it will take me to that image. And so I think it's a really nice way of looking at photo collections. But it's not quite a model, it's placing the photos in context. Okay? So this is what people are already doing with these large collections of photos. So we got interested in making models for a few reasons. One is in order to support our surveillance system. Well, actually, my company, we don't really care about what people are doing in our lab that much. But other places have all these security cameras up. So a typical place is like a Las Vegas casino. And there's some poor person who gets a screen, sits in a room with all these screens, a video feed from sometimes like 200 cameras. And then that person's supposed to figure out if something suspicious happens, what screen to look at next. And so what people at my lab tried to do is come up with a way where if you saw something in one of these images that looked suspicious, you could click on that and then it would guess which images were most likely to be the ones you'd go to next based on which ones were from nearby and which way the person was going and things like that. And we found we actually needed some 3D data that the building plan, the floor plan wasn't quite enough because in things like cubicle areas, or if you think of about a casino floor where there are these huge rooms with all of these tables, it can be hard to locate where somebody is unless you have 3D information about what's in those spaces. So we built a very primitive 3D model. It doesn't look very good because we weren't planning to present that to the surveillance people. Though afterwards we realized some of the people have never actually been in the building that they're doing the surveillance for. So it would be helpful for them to have a nice model to explore. So our initial model just had the basic geometry that we could then feed into the system. But then we wanted to do a more sophisticated model. And that led us into collaboration with a new factory, a chocolate factory that's being built in San Francisco. Then they were interested in having a virtual model of their factory. And in this case, by the way, can everybody see the screen well enough, or should I dim the lights? Dim? Okay. So the virtual model we built up there, that was built in the traditional way by artists who are very good at these modeling tools and had gone in and made measurements and taken photographs, but then they built these models by hand. And we felt there's got to be a better way. But we wanted something that wasn't just a point cloud model like the early ones you saw, where you get points. We wanted something with smoother surfaces. So we wanted polyhedral models with the surfaces filled in. Actually, we wanted something a little more general where we could deal with curved surfaces, but I'm just going to talk tonight about polyhedral models, and I'll explain what that is in a minute. Other applications for the models we're building include training. The military's been doing this for ages. Other people who've been doing this sort of thing include emergency response people, immersive telepresence where people are in different countries and want to communicate about the objects they're working on. Facilities like testing disaster plans, hospitals like this, because it's really hard to actually do an emergency plan drill in a hospital ever. But you can do, if you have a good model, they can even test things like how many people can get through this area without it being a problem, and can we really get people out fast enough. Virtual tourism, which is related to what I showed you at the beginning. Psychiatric treatment, for example, it's helped with people who have fear of heights, for example. So that's some of our So now, that's some of the applications, and now I'll talk a little bit about what some of the mathematics is behind it. Now, most of my talk is just going to be in 2D, partly because that's a lot easier to show on slides, and it will keep things simpler. But one of the things I think you can always be keeping in the back of your, so my feeling about when you listen to a lecture is it's much more interesting if you're trying to think about things maybe ahead of the speaker or related to what the speaker's talking about. And if you know something already, try to think about what's going to be the next step. So in this case, one of the things you can be wondering about is if I show you something in 2D, how do you do the same thing in 3D? So most of this generalizes, but sometimes it's a little bit tricky to see how. Okay. So the models I showed you at the beginning, they were matching correspondence points between images, and then they were getting a point in 3D space from that. So if you have two points that you think are the same, so if somebody has told you, well, this point in the image and that point in the image correspond to the same point in space, then from knowing where the camera is and those two correspondence points just in the image, I can figure out, okay, those two rays through those 2 points intersect at this one point. So that must be where the point is. Okay. Now, the tricky part of this is that you have to know those really are the correspondence points, because in some cases, they might look like they correspond, like these look like they correspond, but I could have taken an image of this object, and these are what my images would look like, but the points I calculated, while they are the border of the red and the yellow in each case, in the two images, the border of the red and the yellow is different, because the red square, the red rectangle, is obscuring part of the hexagon in the lower image. So in this case, those wouldn't be correspondence points. So you have to be very careful. And when they do the matching between these photographs, they have very sophisticated techniques for trying to figure out whether this patch here and the local features of this patch and this other image match. But they get a lot of errors. So then they have to do some algorithms to see what's the optimal placement of these things that still makes sense given what we know from all of those points. And that's how they construct those models. But that's why they're only partially filled in, because they're really having to do a lot of guesswork. So what we want, so the ways people obtain correspondence points are they ask a person to hand mark what they think are correspondence points. And this works pretty well if the images have a lot of meaning to the person, but for really repetitive images, the people may get it wrong. There are these sophisticated approaches I mentioned before, but all of these approaches have difficulties with surfaces like many walls. So most of the applications you'll see of the image modeling are done outside because it's easier. Inside you tend to have a lot of blank walls, and those are very hard for the image methods to pick up any features to try to match, because everything matches to everything else. And black is particularly hard because even if you light it really well and you have two surfaces coming in at an angle, you may have trouble seeing that, even in good lighting, seeing the edge. So we said, well, we'd still like to be able to model solid color black objects. So how can we do that? Well, we did what a lot of people think is kind of a cheat, and we just put markers on them. And then we took our images. And so our goal was to make it quick and easy for a person to create a rough model of a space or object by placing markers that have meaning and taking images. So the meanings might be these markers are all on the same wall, and since it's a wall, it should be vertical. So if you get things that are a little bit skewed, let's correct that. So we also have things that indicate dynamics. I'll show you some models near the end. What I'm going to concentrate on is just reconstructing the geometry, because we also have appearance characteristics, but just reconstructing the geometry. So what our system does is it takes these markers that have these interesting patterns, and each one has a unique pattern. So, and you don't see patterns like this very much just in every day. So if one's there and you can detect it in the image, then with high probability that really is a marker you placed. And you can do this for a large number of markers, and you can estimate all the marker and camera positions from just knowing where a few of the markers are to begin with. It's very similar to doing the correspondence points, but in this case, you even know the size of the marker. So you can get the four corners and be able to deduce where the marker and camera. So what we want to do from that information is build a 3D model. So what are some of the things we can mark? We can mark vertices, corners of things. We can mark edges. We can mark planar surfaces. I won't talk about this today, but we can mark cylinders, things like that. And from just small amounts of this data, we want to be able to construct a model. So I'm first going to talk about how to reconstruct a model if you know just where the vertices are, because that's what people had done mostly. But we didn't really like the idea of just doing vertices, because for some of the models we're trying to build, vertices are kind of hard to reach. Like, I don't really want to have to put a marker up in that corner if I can help it. I would like to just be able to put markers on these walls and be able to deduce where they intersect. So I'll first talk about reconstruction from vertex data, and then I'll talk about reconstruction from the sort of data we get out of the marker information. So we not only get where the marker is, but we get its orientation. So the position together with its orientation is called the pose. And because we know the camera is looking at it from a certain, we know what the pattern of the marker is, and we know it's not this way. So we know the camera was looking at it from this way. We also know the vector that points out from this surface in a perpendicular way. So from that, we'll try to do some. And what was really surprising to me is that this is very simple in some ways, Euclidean geometry. But people hadn't at least written papers explaining how to do some of these things. So I had to spend some time trying to figure out what can be done, what can't be done. When you have certain data, when you have a certain set of data, it might be possible to have 5 models that all mesh with that data correctly, but do not give you the one that you had started out with originally. So under what circumstances can you mark something and know that you get the model you intended back from the data? That's the question we're trying to solve. So our system, we have a number of things we can do. But before I tell you some of the reconstruction thing, I want to give you some basic definitions. And some of these, some of you will have seen, but I want to go through them all, partly just to make sure everyone's seen them, and partly because, to my surprise, some really basic ones have multiple definitions. There isn't a standard one. So, for example, polygons. So I really thought that a polygon, there'd be a totally standard definition for what a polygon is. But it turns out there are some differences of opinion as to whether you should consider some odd edge cases to be polygons or not. So I'm going to call a polygon a closed, so that's a finite part of the plane which includes its boundary, connected, so you can get from any 2 points to the other. Some of these I'll review again. 2-dimensional, so it's in a plane, whose boundary consists of a finite set of segments, edges, and whose endpoints are called vertices, and there's a vertex between each of the edges. So, and they don't, the 2 edges don't intersect. So one of the reasons that people disagree about what the definition is that sometimes you could have 2 polygons touching each other in the middle. So like a vertex of one could be touching another in the middle of an edge. Should that count as 1 or 2 polygons? Or 2 edges could touch each other but not quite together. So when I give you a definition like this, there are lots of questions you can be thinking about. So what are the simplest polygons you can think of? So you have some examples. What are some complicated polygons you can think of? Can polygons, according to this definition, have holes in them? So I thought I might see if some people wanted to come down and help me out here. So maybe I'll turn some of the lights back on. And what I'm going to ask some of you to do is I'd like all of you to be thinking about this, but I'd like a few brave people to come draw on this board some polygons so we all know what we're talking about. And I want you to draw both some of the simplest ones you can think of and also have fun and draw some of the most complicated ones you can think of. And over there I want people to draw some things that people might think are polygons but are not polygons. So do I have any volunteers? Great, come on down. Come on down. Come on down. Yeah. Whichever one you want. Anyone else? I think we can. You can draw more unless somebody else is going to come help out. Anyone else? Good. So I'm going to take a poll. Who thinks this is a polygon, or sort of leans that way? Who thinks it isn't? And why?
Was it not connected?
Yeah, see, most of these questions are going to have right answers on both sides. So it depends how you think about these things, which is one of the reasons why mathematicians insist on people being precise. Because most of us think this is a polygon. I mean, I kind of thought it was a polygon because I think of it as being a triangle and this edge is connected to this edge. But they didn't quite get connected. So I still think it's a polygon because we all picture it in our mind as the perfect triangle. And we're just thinking the drawing wasn't quite right. But you're right. It's, it's not. So what about this one? Who thinks it's a polygon? Who thinks it isn't a polygon? Okay. And does anyone have any other reasons for thinking that it's not a polygon other than that the edges don't connect? Yeah?
One of the edges is extended too far.
Yep. Yep.
What if the edges look slightly curved?
That's another good reason. It's very hard for people to draw a completely straight edge, okay? But when we think about these things, we mostly think of them as being completely straight. So our ideal version of this is definitely a polygon. Whether the actual drawn one is a polygon, well, as you mentioned, slightly curvy, edges extend, but I'll still take it as a polygon. What about this one? Who says yes? Who says no? Okay, why is that?
Just in the curving and everything. Because nobody's perfect, so nobody can draw perfect polygon.
Yeah, yeah. Any new reasons? Yeah?
One of the edges was drawn twice.
Ooh. Yeah, I think they meant to erase that one, but yep. So one of the difficult things for mathematicians is that we like to be very precise, but we live in the real world. So this is a constant problem. So what about these? Who thinks this is a polygon? Nobody. Yeah?
Apart from drawing defects, yes.
Yeah? Explain.
It isn't actually curved. Think it really low level. So what I would say to sort of extend that is if I saw this on a computer screen which only has very specific dots, then how can it be a completely smooth curve, right? So it must actually have lots of little straight edges here, just so small you can't see, okay? But that's not how we're thinking of this. We're thinking of it as a totally smooth curve. where none of it is straight. So again, this is terrible. I'm not sure I'm going to give you any questions that have just one right answer, but oh well. What about this one? Who thinks it's a polygon? Okay. Anyone think it's not a polygon? And somebody thinks it's neither. That's interesting. Why's that? What's that? Ah, the layer of chalk comes out of the board. That's a new one. I hadn't thought of that one before. Yeah. I thought you were going to say there's one edge that's straight, so it's sort of a polygon over there, but then there's a curvy edge here, so that's not a polygon. So overall, it's not a polygon because all of the edges would have to be straight. What about this one? Who thinks it's a polygon? Okay, who thinks it's not a polygon? Okay, well that was boring. What if I draw this one? Who thinks that's a polygon? Who thinks it's not a polygon? Okay. Why do you say it is a polygon?
It didn't have any curved lines, and it was all the edges were connected.
Okay. Yeah.
Not a polygon because if you really look at it, this thing in the middle makes it 3D.
Ah, yeah, it could look like it was 3D.
Middle basically makes it if it's a hole or sticking out. And
Okay.
if it's a hole, then it's 3D. If it's sticking out, it's 3D. Yeah, so actually, you said that in this, your definition said that it has to be a connected region, and then so the inside one is not connected to the outside one. Mm-hmm. I'll get from the outside to the inside.
Yeah, so one of the things that I wasn't very clear on is what is this the boundary of? And I said it had to be a two-dimensional region, and I didn't actually specify. In none of these did we draw the inside. But in this one, it's helpful to draw the inside. So this is what I'm thinking of as the region inside. Yeah?
In your definition, the edges E1, E2 have to be sequentially connected. And that is impossible here since there is at least
Do you want to come up and point?
pair that's not connected, that is jumping from the outside to the inside.
Yeah, so you can't get from these edges to the inside. So did I leave my So if you look carefully at the definition, you have to have a chain of edges connected by the successive vertices. And if I go around here like this, I can't connect this edge to this. So this is one of those cases where people might disagree because all of the sides are straight. Okay. What about this one? Yeah?
There's two explanations. The first explanation is that that middle point is a vertex. If that is a vertex, so it says each vertex is at the endpoint of two edges. And then, so that vertex would be at the endpoint of four edges, which makes it not a polygon.
Yep.
Or you would say that point is just a random intersection, which would make it so that it says that,
Non-consecutive edges do not intersect.
yeah, okay, yeah.
Excellent explanation. Yeah?
Or you could take it as two vertices infinitely close together.
Yeah. Well, because of the way it was drawn,
It's still not a closed, connected, two-dimensional region.
That's right. But it might be 2 polygons if there's a little bit of space here that we can't really see. Yeah?
I have a question going back to the curve.
Yep.
If you like zoom in like close enough, eventually like is it just like connected like dots, I guess, like making it like a line, or is it still considered a curve?
Well, I don't want to get into quantum mechanics because that wasn't the point of my talk. But but this world's really weird. So for a while, depends what scale you're on, okay? So, and it depends how it's drawn. So for example, if it's a digital thing, as I mentioned before, it probably has all sorts of little line segments as it goes through. Now, if you have some real life thing, it might be really, really round. You might have machined it and sanded it and things so that it's really, really round. But if you go down to the atomic level, who knows I mean, then it's all sort of a separate set of points, except they're really clouds. I don't even want to try to talk about the geometry there. Yeah? Somebody else had their hand up? Okay. So that was probably more about polygons than you expected. It's more complicated than you would imagine at first. Oops. So I also want to talk about 3 dimensions. So polyhedra, which is the plural of polyhedron, are like polygons but in 3 dimensions. So, and they have boundaries consisting of a finite set of faces, and the faces have to be polygons. And I wish I had enough time to have everybody come up and draw polyhedrons. I'm not going to have everybody do that, but everybody can think about what polyhedron they would draw and what are the funny cases. Okay. So in particular, you can think about what are the simplest ones you can think of, what are the most complicated ones you can think of, and it's always good whenever you see a definition to make sure you can think of some things that aren't whatever the definition is. And also, what are some confusing edge cases? And you guys were really good at doing that for polygons, so I'm pretty sure you can do it for the 3D case too. And we already covered most of these things, so I'm not going to go into that. Okay. So I'm going to define a few other properties of polygons or polyhedra that are useful. So one of them is convex versus non-convex shapes. So a convex shape is just something where if you take any 2 points in that shape, any 2 points, then the line between them is still in that shape. Okay? And non-convex just means that there's some pair of points where the line segment goes outside the shape. And I gave you a cartoon by a friend of mine, Tom Cannell, to help illustrate the a regular polygon, which is really, I mean, it's more than just convex. It has the same angle at each edge, at least if you don't look at the diagram too closely. And then there's the other one, which is non-convex. Why is it non-convex? Say that louder.
It has reflex angles.
Okay. Can you be more specific related to the definition here?
Want some help? Go ahead here.
Well, on the left, that angle over there, you can draw 2 points that where the line would go out of the shape. So it's,
So you're meaning like here and here?
yeah.
Yep, exactly. Okay. So that's not convex. Okay. Is this room convex? Why not? Why not? Somebody in the back. Oh, nobody in the back. Oh, there we go.
The ceiling is kind of in a step form. So the highest point here, go on this lower point here, that's outside the roof.
Good. Yeah. So now when you get bored, you can go around the world whether the rooms you're in are convex or not. And this is actually useful to know for modeling because non-convex rooms are harder to model from these image-based approaches. Why would that be?
Just flat places you can't see.
Right. There are many more places that there are many places where the camera can't see certain things, so you have to make sure you take things from lots of different angles. Okay. I'm also interested in orthogonal shapes and polygons. So an orthogonal shape is something where all of the edges are aligned with the axes. Okay. And again, these are very common in the real world. Like this front table is, if you don't look too closely at it, is orthogonal. But the room is very much not. But I didn't know before I came here whether it would be or not. And we mentioned connected. Connected means that for every pair of points, there's a way to get from one point to another within the shape. Now, what's the difference between connected and convex? So can a non-convex shape be connected? Well, how can that be if the line segment between two of the points goes outside the shape?
Just as a path, it doesn't say a segment, so you have a curved path.
Yeah, so if we go back to this guy, we couldn't go in a straight line from here to here, but we can go through that way. Right, exactly. Okay, so starting with these basic concepts, I want to try to do some reconstruction. So there's a theorem by ORourke that any orthogonal polygon can be unambiguously reconstructed from its set of vertices as long as it doesn't have any degenerate vertices. The degenerate vertex is one that has a 180-degree, so it really could just be one edge, but you've stuck a vertex in the middle. Okay? So if it doesn't have that, then at any vertex, because it's orthogonal, there are only 4 possibilities of how the edges can come out of the vertex. And because there are no 180-degree ones, for each vertex there's exactly one vertical edge and exactly one horizontal edge. And he's actually able to do, his theorem works for a more general class of things, more than just polygons. It also works for collections of polygons and polygons with holes in them. So whenever I say a theorem like this, you should think about, okay, how would I do this?
Why is orthogonal required? And why did he rule out 180-degree vertices? Okay, and also, what about the 3D case? So here's an example. How would you figure out what set of orthogonal polygons, possibly with holes, this is the vertex set of? Anyone have a guess? I wish I could give you more time to think about it, because he came up with a really elegant and simple solution that works generally. But on the other hand, he published this paper relatively recently. So this is a new result that got published in a paper that's very simple. So what he says to do is, well, we know that out of each vertex, there has to be an edge coming out of it. So if I take the very top leftmost vertex, well, I know there aren't any vertices to the left of it, so it must connect to the right. And so I can keep doing that. I take the first vertex and I connect it to the right. And then if there are any others in the row, I connect those to the right. Otherwise, I move down and I just connect things from the right. What does he do for the top to bottom ones?
Pretty much the same, except it's instead of left and right, you kind of turn the thing 90 degrees and you think of it that way.
Exactly. So that's what happens. And if you put it together, that's what he got. So he can deal with holes, he can deal with non-convex, and all it came from was these things. So that's simple and something that was published relatively recently. So why is orthogonality required? Anyone know? Have a counterexample? I'll give you a hint. Can you think of more than one way of making this the vertex set? Can anyone describe it? Should I just tell you? So that's why he requires orthogonality. Why does he say you can't have 180-degree vertices? So I gave you a big hint by putting in, yeah?
Okay, so there's a few ways you can do this. If you can take that big rectangle.
Yep.
And then you can also wait.
So for this one, it's helpful to remember that I'm letting it be multiple polygons.
Oh, okay. So then it can be 2.
Right, so then it can be 2. And you can construct more complicated examples where it will just be 1 in both cases. So I'll let you guys figure that one out. So there's a 3D version of this, but again, I'm going to let you guys figure that out. I'm going to very briefly, in the last 3 minutes, talk about what happens from the markers. Okay, so I want to be able to put up markers on each of these walls, just slap them up somewhere in the middle. So I want the person who's putting these up to put at least 1 marker on each wall. And that's all I want to require. And that works for any convex polygon. And basically the reason for that is that the edges of a convex polygon split. So a line segment that's an edge extends into a whole line that splits the space in half. And for any of those,
a convex polygon lies on one side, and then you can take the intersection of those, okay? But for other cases, there are lots of examples of why this one marker per edge is not unique. So here's one that's a little more complicated, but along the same lines as the one you just saw. So in this case, I'm just going to tell you, since we're short of time, you can put this as two rectangles, or you can put this as two rectangles that are connected by an L, okay? So there's the connected version, and there's the two separate ones. But I want to know, can I have something that's basically the same shape? So it's one thing and could be transformed into itself just by, well, it's topologically the same, okay? So, and by the way, this extends to the 3D cases. So here's one where we can get the same topology, but in two different ways. And I basically just extended the example we just saw, where on the left I have a rectangle, on the bottom I have a rectangle. And so it depends whether I connect those two. So I basically was able to take this very simple example and turn it into something more complicated. So it can either be this, or it can be this. Okay. Now what about for multiple convex polygons? So we were able to do it for a single convex polygon, but what about for multiple ones? Can anyone see how to fill this in two different ways? I'll give you, yeah? I'll give you a hint. Can you think of 4 triangles? That's indicating that that's pointing to the outside of the shape.
So the markers are on that point?
Say that again?
So the marker is on that side?
The markers mark the edge of a shape, and then the arrow says, I'm on the outside of, I'm pointing to the outside of the polygon, not to the inside. Ready? So the green ones form one set, and the blue ones form another set. And somebody might have thought of it before, but I had to come up with this because for a little while we thought maybe it would work for multiple convex polygons. It worked for some cases, but we wanted to have an algorithm that we can give to other people and say, this will always work for you. That's what a mathematician does at a company like mine, where we do software, among other things, is we make sure that when somebody says this will do something, that it really will do that thing, that it doesn't just do those things in the few cases we tried. Because the first algorithm some people came up with to do these things worked on the first few cases they tried, and then didn't work on the next one, and then they did something else, and it worked on that one, but then it didn't work on the next one. So then they asked me to look at, okay, let's see if we can find an algorithm that's provably works here. So I had to come up with a more complicated way of doing that, and I'm not going to spend time on that because I'm already over. But you can email me or read my papers or whatever about that. Okay? Here are some models we made with our markers. So top's the picture, bottom's the model. Here's of our lab. And here's of the bookcase that we started with. And thank you very much for having me. This was all about Euclidean geometry, and I hope that the talk didn't fall flat.